Good morning, everybody. This is a lesson for my intro calculus students. This is our, I guess, third day on implicit differentiation. And today we're probably only going to get through one example, but it's a big example. You're going to need some loose leaf too, because I'm going to kind of go a little beyond what's in the notebooklet here. So we're on this page here. Example, find the equation of the tangent line to that curve. I'm going to actually call this part A too, because we're going to do a B part, and like I said, you're going to need loose leaf for the B part. So find the equation of the tangent to the curve. So here's an ellipse. There's the equation that describes the ellipse, and at the point 0, -6, I would like the equation of the line that touches that exactly once. So how are we going to do that? We're going to use implicit differentiation. Why? Because it would be very difficult to isolate this equation for y. So here we go. We would like the derivative with respect to x for this entire equation. That means both sides of it. And the first couple terms are easy. The derivative of 2x squared is 4x. The derivative of 3x is 3. But then remember, I have to consider this as chain rule. Y is an inside function, and of course squared is the outside function. So derivative of this thing, using chain rule, is 2 times y times the derivative of what's the inside function is, which I actually don't know. So I'm just going to call it dy dx. Same thing for the next one. I'm going to call that 4 dy by dx. And of course the derivative of 12 is 0, and the derivative of 0 is 0. So there's my equation. Now, what I want is I want the slope at this point. Actually, I want the equation for the slope everywhere around the curve. So I'd like to isolate dy by dx. So everything that isn't dy by dx moves to the other side of the equation. And it's going to become negative for both of those terms, negative 4x minus 3. Now I can factor dy by dx out, leaving me 2y plus 4. And then I can divide both sides of the equation by the thing I've factored out here, 2y plus 4. And that's it. That is the slope everywhere around the curve. So now I want dy by dx when x is equal to 0, right? Because as you can see up here, 0 is the spot that we're looking for on that. So this thing here has an x of 0, which makes this negative 4 times 0 minus 3. And oh, right, and of course, y is negative 6 when x is 0, right? Should have highlighted both coordinates of the point there. So 2 times y becomes 2 times, 2 times y becomes 2 times 6, or sorry, negative 6. And I end up with negative 3 over negative 12 plus 4, which is negative 8. Which simplifies to 3/8. So this thing here represents the slope everywhere around the curve, but at this one point, the slope happens to be positive 3/8. So I just use my grade 10 skills now. I have a slope of 3/8. I have the point 0, negative 6, and y minus negative 6. Let me erase that. There we go. Is equal to slope times x minus 0 times both sides of the equation by 8 if we're going to go to standard form. And 6 times 8 is 48 equals 3x. And so that gives me the final equation, 3x minus 8y minus 48 equals 0. And there we go. Solved. Let's check that out on some graphing software. let's see, there's the blog, there's the graph. So first of all, there's my ellipse. There's the point that I'm looking for. And let's see, does this look like, now actually, Desmos can't do implicit differentiation, unlike the curves that were explicitly defined, where you could ask it to find f primed of x or y primed. Desmos can't actually do the calculus for us. So our only way to check the answer is to actually find this equation and then just kind of do a quick look. Does it look like it's a tangent line? If I was off even a little bit, if I'd have goofed up, say I thought that 6 times 8 was 54. I've made that mistake before, I don't know why. But say that I thought that. Then, aha, doesn't even hit my line. How can that be a tangent, right? So, to check, I'm just going to zoom in. Does it look like it hits this place only once? And yes, it does. No matter how much I zoom into it, no matter how much I zoom in, and I can keep zooming. I'm using a touch screen, but I can also just zoom in and out like this. No matter how much I zoom into it, it doesn't ever look like it crosses and touches it more than once. I'm getting one dot. That's Desmos' way of telling me it only touches it once. Okay, so there we go. We can be fairly sure we've got the right answer for this one. Now, like I said, the book moves on to new examples. I want to stay with this question, and I'd like to go to, and we'll add a part B here. So if you have some loose leaf or something, here's what we're going to do for part B. Find the domain and range of this ellipse. Unlike a parabola, which has a domain that goes on forever in both directions, an ellipse is bounded on all sides, right? So find the domain and range. So jot that down. Find the domain and range of the ellipse in part A. And let's think about this. Look at the diagram here. What do we know about this thing? Well, what we know is that the domain will be, let's do the domain first. The domain will be whatever is between the line that hits that and the line that hits that exactly once. And the range will be the values between here and here. I'm actually trying not to hit the same point. So these, of course, are my maximum and minimum x and y values. Now, how do I find those? What do I know about the slope of this line? That has a slope of 0. So does this one. So my range will be bounded by the two places on here where the slope is 0. What do I know about these guys? Let me use a different color. Let me use blue. What do you know about these guys? What's the slope here? That's an undefined slope. So my x, my domain will be bounded by x values that give me slopes that are undefined. So with that in mind, let's see if we can solve this. So we actually already have an expression for the slope, right? dy by dx is equal to negative 4x minus 3 all over 2y plus 4. And to find range values, we'll do range first. So the range boundaries are when dy by dx is equal to 0. So we set this to be equal to 0. We multiply both sides of the equation by 2y plus 4. And then we solve for x. So x is equal to negative 3/4. But remember, the range is the y values, right? So I need to know what are the y values when x is negative 3/4. So in other words, what we've just found is that we have found that this point and this point has coordinates of negative 3/4 for x. But we need to figure out the y coordinate. How are we going to do that? We have to go back to the original equation. So my original equation was, of course, 2x squared plus 3x what was it again? Plus y squared plus 4y minus 12 equals 0. And we need to solve for y when those x values are negative 3/4. And no, a first-year university course would not give you a calculator to do stuff like this. So you're kind of on your own. And notice it actually asked for exact answers. That means leave it in radical form. Do not round it to some decimal approximation. Okay, so how do we do this? Well, let's see. 3/4 squared is 9/16, right? But you're timesing by 2, so that's going to be 9/8. Then here you have 9/4. And I might as well move the 12 over because all of those things are a constant. I'm going to have to combine them together. And okay, so how do I get that all as one thing? Well, let's see. 8, 4, and 1 have a common denominator of 8. Right? So this is going to be, and let me rearrange it again. Let me put the constant at the end where it probably belongs. So I have a common denominator of 8, so 9/8 is already in that denominator. 9/4 would be 18/8. And 12, what's 12 times 8? 96? And so we have negative 9/8 minus 96 more eighths is going to be negative 105/8. Okay, you should have 3 tools in your toolbox from grade 11 that you could rely on here. I think factoring's out. I don't want to try factoring with a fraction. And although I can get rid of the fraction fairly quickly. I can multiply everything in the equation by 8. That might make my life a little easier, actually. But I still don't really want to factor that. 8 times 105, and then when you get that answer, what 2 factors of that make 32? I don't think you're going to find such numbers. I have a feeling we're going to be looking at a radical here. So forget factoring. Completing the square is only a strategy I use when not only do I want to solve it, but I might want the vertex too. I don't care what the vertex is. I just need to solve for what this y coordinate is. So what does that leave in our toolbox as the best tool for this job? We're going to use the quadratic formula. So a little quick reminder that the quadratic formula is, in this case, it's solving for y. So y equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's plug in the numbers that we have here. We have y equals, and b is 32, so negative 32 plus or minus the square root of 32 squared minus 4 times 8 times negative 105 all over 2 times 8. Okay, so again, we don't want a decimal here, so I don't know that I'd reach for my calculator. So I might have to do some scrap work, but it turns out that this turns out to be negative 32 plus or minus, and after a little bit of scrap work on some scrap paper, I found out that this is 43/84. And of course 2 times 8 is 16. And it makes sense that there's going to be 2 answers for the plus and minus, right? Because remember, we're finding the y coordinates here and here. So yep, there's going to be 2 of them. And we want exact values. So I kind of already have an exact value, but I can kind of tell that this simplifies. This for sure has a 4 in it because it ends in 84. It might even have a 16 in it. Let's see. I don't remember. I might just cheat here and grab my calculator. Does 43/84 divide by 16? Does 43/84 divide by 16? Yes, it does. So this is negative 32 plus or minus the 16. Remember how to simplify a radical? The 16 comes out of the radical and becomes a 4. And then that leaves me 274. I don't think 274 has any more perfect squares in it. It doesn't have another 4. It doesn't have a 9. And it doesn't have a 25. And it couldn't have a 36. I think we're good. All over 16, and then one last step of simplifying. You could factor a 4 out of both of these things. So you have yourself negative 8 plus or minus, actually, wait a minute. Let's do this better. We can factor a 4 out of both of these things. So take the 4 out, and you have negative 8 plus or minus root 274 all over 16, and then 4 goes into 16 4 times. And then I think for my final answer, I'll just divide both of these things by 4. So I have negative 2 plus or minus a quarter of 274. So there it is. Those are the two y values. So that's my range. My range is from negative 2 minus a quarter of 274 to negative 2 plus a quarter of root 274. And that's my range in exact values. And I'll double check to make sure that I got that right using some technology. When I did my little Desmos file, let me get the tangent line kind of out of the way for now. So there's negative 2 plus a quarter of root 274. So that should be the line that's on the top. There it is. Looks pretty good. And the negative version of that, or the minus, should be on the bottom. And again, zoom in, and you'll see that, whoops, I said zoom in, and you'll see that it should only just touch it. It shouldn't cross it more than once. It's looking pretty good. So I think we got it. All right. We still have to do the other one, though. What about the domain? So the domain is going to be whatever is between the maximum minimum from the left and right. What do we know about those guys? That's where the slope's undefined. So we'll just kind of do this the same way. So I know that my slope is dy by dx. And it's negative 4x minus 3 over, what was it again? 2y plus 4. And we want to know, where is this slope undefined? And this slope's undefined when? When is a number undefined? When you divide by 0. So set this to 0, which means that 2y is equal to negative 4 and y is equal to negative 2. And now it's the same trick. Unfortunately, domain is the x values, so I have to do the same thing I just did. So I have to now find the x values when y is equal to negative 2. So what we've just done is we figured out that these blue lines here have a y value at this point of negative 2. I need to find their x coordinates. Once again, I'm going to be playing with a quadratic, right? I go back to the original equation, which was 2x squared plus 3x, what was it again? Plus y squared plus 4y minus 12 equals 0. I probably should have done this one first because it's easier. You don't have to deal with a fraction. So what's x when y is negative 2? Okay, when I square a negative, I get a positive. So that's going to be 4. That's going to be minus 8. And that's going to give me 2x squared plus 3x. Let's see, 4 minus 8 is negative 4, minus 12 more is negative 16. And once again, I'll try factoring. This time the numbers are smaller. Maybe it factors. 2 times 16 is 32. Are there two numbers at times to make negative 32 that if you add them you get 3? No, I don't think so. 1 and 32, 2 and 16, 4 and 8. I'm out of options. Nope. I'm afraid we're going to have to go back to either completing the square and solving or the quadratic formula. I choose the quadratic formula. So in this case, whoops, come back here. X equals minus b plus or minus the square root of b squared minus 4ac all over 2a. And that's minus 3 plus or minus the square root of 4 16s is 64. 64 doubled is 128. The negatives will cancel, so it'll be 128 plus 9 all over 4. And I don't think this one simplifies the way the other one did. I think this one's just done, right? Because I don't think there's any perfect squares in 137. Let me think about it. What could there be? No, there's no 49s. All the even ones can't be possible. So no, that's it. That's as simplified as that one's going to get. So therefore, the domain goes from the negative answer to the positive answer. Oops, and I wrote it wrong. And that's it. I like that problem. Kind of rolls together our grade 11 skills along with our new calculus skills. And once again, just before we leave it, let's check to make sure that that looks right. So I graphed, let me get rid of the horizontal lines. So I graphed these as vertical lines. Remember, vertical lines are always x equals. So I have x equals the left one, looks pretty good, and x equals the right one. Yep. So my domain goes from here to here. And oh, there we go. You could run that through a calculator and see if that's the same decimal you get from that radical, but I'm pretty sure we got it right. So there we go. All right. So that was the only example I was going to do today, so I'll wrap it up here. If anybody's stuck on any homework questions, I'll take a few homework questions before we run out of time. But otherwise, thanks for watching.